Okay, Quiz 12, special gas law problems. The partial pressure of methane, nitrogen, oxygen gas in a sample were found to be 100, 450, and 200 millimeters, respectively. Calculate the mole fraction of oxygen. Okay, by definition, mole fraction is the moles of the individual component divided by the sum of the mixture, moles of the mixture. That can be rewritten as the moles of the component divided by moles component 1, moles component 2, on up to moles of component N. In the gas laws, we can calculate moles through the ideal gas law, PV equals nRT. Solving for the moles N, we have PV over RT, like this. Now, applying this expression for moles into the mole fraction equation, we can say that the mole fraction of an individual component, being Ni over the, say, total number of the sum of the moles, is pressure of the individual component times the volume that is surrounding the component divided by RT, divided by pressure total V over RT, and noting that RT and V are constants, we have the individual pressure divided by the total pressure will give us the mole fraction. Now, the individual pressure for O2 gas was given to be 200 millimeters, and the sum of the pressures, that is the total pressure, is equal to 100 plus 450 plus 200 millimeters, and that would be equal to 750 millimeters. So now we can take the individual pressure divided by the total pressure and have the mole fraction. So the mole fraction in terms of the partial pressures, pressure of O2 divided by the total pressure now is 200 millimeters will cancel out over 750 to equal 0.267. And that would give you B choice in that problem. Problem 2, a reaction system that undergoes a gain of energy would be classified as endothermic, exothermic, isothermic, or exogonic. By definition, processes, physical or chemical processes that lose energy are classified as exothermic reactions, and in the same context, process that gains energy is classified as endothermic. Just to add to the definitions, isothermic means that a change in energy has taken place, but we wind up at the same energy at the end of the process as we started with. In this question, the reaction system that undergoes a gain of energy would, of course, be the endothermic process here, so endothermic is a choice. Now, it's very important that you understand that the terms exothermic and endothermic are defined relative to the reaction system or the object of interest in the research. So note, endothermic and exothermic terms are defined to the system of interest. In our case, chemical reactions or physical reactions that are undergoing an energy change. This idea is sometimes related to this diagram, T-table, which is headed on the left by the system, which is the object of interest that we're trying to study, and on the right, surroundings, which essentially is everything else. So if we set a hypothetical issue, say this represents the system or a chemical reaction right there, if the reaction loses energy, if it loses energy, we find the energy flow moving from the system into the surroundings. The indication here is exothermic. Now, while we define the term in terms of the system, notice that if we look at the surroundings, it's endothermic to the surroundings. Now, that emphasizes the point that you must remember that when using these terms, it refers to the process that you're studying. And just as for endothermic, if the system is the object of interest, then endothermic would mean that the system of interest is gaining energy, but it's exothermic to the surroundings. Number 3, a gas has a density of 2 grams per liter at 0 degrees and 1 atmosphere. If the temperature is increased to 25 degrees, what will happen to the density? Will it increase? Will it decrease? Or will it remain unchanged? As a direct answer to this, the density will decrease for a gas as the temperature is increased. And of course that would give us B choice and the answer choices. if we take the density as the mass per unit volume and compare the mass per unit volume at one temperature to the mass per unit volume at another temperature, then we can prove the density will in fact have decreased. Now, if we consider the following: mass is a constant, and temperature 1 is, say, 0 degrees Celsius, 273 Kelvin, and we're changing to T2 to equal 25 degrees Celsius, 298 Kelvin, like this. And simply put, from Charles' law, volume change is proportional directly to changes in temperature. And so we find that volume change is equal to a constant times directly proportional to temperature. So if we increase the temperature, we will certainly be increasing the volume. So if we take the density is equal to a constant mass over volume 1, density 1, and increase the temperature 25 degrees C, then what will happen to the denominator here, density 2, will go to, well, volume 1 will go to a larger volume at a constant mass. As we increase the denominator and the ratio, the function density 1 will decrease to density 2. So increasing volume gives decreasing density. Okay, now for question 4, what is the molar volume of CO2 solid at a minus 78.5 degrees Celsius and 1 atmosphere? Well, first of all, the idea of molar volume refers to gas phase substances. The indication here is that CO2 is a solid. So if CO2 is a solid, molar volume is in fact 0 and does not have a volume. It gives us a choice in that. Now give this to focus your attention on when an equation is given. Be sure you not only notice the substances and the ratios and quantitative issues, but also note the state of existence, because it certainly can have an influence on the outcome of your problem. As an example, look at these two reactions representing the combustion of methane. Here CH4 reacts with O2 to produce CO2 and water, and I show the same issue in the second equation. However, in the first equation, it's showing to produce a gas phase, or water gas, as some people call it, component, whereas the component listed in the second equation is a liquid. And this will certainly have an impact on solving some problems, especially when you're working with thermodynamics. Here we're looking at 3 molar volumes against 3 molar volumes on the product side, but here 3 molar volumes on the reactant side does not match the molar volumes. There's only 1 molar volume on the product side in the second case. So the emphasis here is that you please make note of the state of existence as you go through and work problems associated with gases involved in process. The last question comes from the kinetic molecular theory, in which we consider those factors which are required to initiate and sustain a reaction from reactants to products. So from the kinetic molecular theory, we read that 4 factors are required to initiate and sustain a chemical reaction. And if you remember, I gave you a simple acronym, CENT, that could help you remember these items. Concentration, effective collisions, naturally reacting substances, and temperature or energy factors necessary to push the reaction beyond the activation energy. In the first case, this defines kinetic feasibility. Reactants must be able to find one another in order to react. That's a fundamental truth, that if the concentrations are so low that A can't find B in a reaction process, the probability of producing products is very low. Effective collisions, because of the three-dimensional nature of chemical structures, molecules have to collide in a certain orientation in order to initiate formation of intermediates and finally products. So orientation of the collisions. Of course, nature or naturally reacting species have to be certainly present. Or naturally reacting substances and in the container, and you must have enough energy, temperature energy, in the reactants to initiate or the chemical process, and this is related to what we call the activation energy. Now, at the activation energy, we find that the gas particles have the greatest probability of having all 4 of these events occurring simultaneously. This can be shown in a Boltzmann distribution. This is an example of a statistical distribution of particle energy. Sometimes people will present this with particle velocities, and is a statistical distribution of all the particles in a given container. At temperature 1, we find that the majority of the particles are located under this curve, as shown, as drawn. Now, if we change the temperature of the system by increasing the temperature to T2, which is higher than T1, let's just put T2 up here, greater than T1, like that, then what's going to happen is more of the particles under this larger area are going to shift to the red line. This red line is the activation energy needed to start the reaction, or the point where greatest probability of these 4 events occurring exist. Sorry, I ran off the plate. Anyway, the red line is the energy necessary for the particles to have the greatest chance of reacting to produce products. But anyway, if we look at a higher temperature, we will see a number of the particles that were in here begin to shift over toward the activation energy, and you will see quite a bit more particles having the capacity for achieving the 4 requirements to initiate reaction. That's why we increase the temperature. We bring the system closer to the activation energy. So all of these will be required in trying to get a reaction to proceed. Now there's some other factors diagrams that you need to be aware of. The transition state diagram, which shows the transition through the activation point and the initial and final energies of the reactants against the products, and these can be diagrammed for endothermic and exothermic products. Okay, just to illustrate very quickly, the transition state diagram for water going from liquid phase into gas phase has a heat of reaction of about 44 kilojoules endothermic. The plus indicates endothermic, and it can be written detached from the equation by semicolon delta H reaction equals plus 44. You don't have to put the plus in that, but if you incorporate it into an equation, you need to put the endothermic value of heat of reaction on the reactant side. The transition state diagram for this would illustrate, starting with water in the liquid phase has a energy content of 285 kilojoules. And if we put in 84.7 kilojoules, it goes through the transition complex or the activation point and transitions into the gas phase. And it will drop about 40 kilojoules between the activation energy and the gas phase. Anyway, the difference between the gas and the liquid phase is 44 kilojoules, which is the heat of reaction. Like that. Now here are the exothermic reactions. Here's synthesis of ammonia. Heat of reaction is minus 91.8 for 2 moles of the formation of the ammonia. If we were to integrate this into the equation, we'd need to write 2NH3 gas plus 91.8 kilojoules. Having the energy number on the right side of the arrow, the Yields arrow, indicates exothermic reaction process. So drawing a diagram of it, we put the reactants at the 0 because these are basic standard state and they go through whatever activation energy. I pick 50 kilojoules just to indicate it, and once it passes the activation complex, the activation energy changes take place that make the products, which wind up at a lower energy level. That is the difference between the energy level of the products and the starting, and the products and the reactants is heat of reaction. Now this represents 1 mole. Of course, the equation is showing 2 moles. At any rate, that's how transition states diagrams are presented.